Hello everyone, we're going to go over chapter 3, section 3.1, and in this section we're working on the basic concepts of probability and counting. There are several objectives in this section. You're going to learn how to identify the sample space of a probability experiment and how to identify simple events. How to use the fundamental counting principle to find the number of ways two or more events can occur, how to distinguish among classical probability, empirical probability, and subjective probability, how to find the probability of the complement of an event, how to use a tree diagram and the fundamental counting principle to find probabilities. I know that is a lot. So make sure that you have time. You can pause the video if you as you watch this. So that is the beauty of this recorded PowerPoint. So we'll start with the probability experiments. Probability experiment. It is an action or trial through which specific results, counts, measurements, or responses are obtained or collected. An outcome is the result of a single trial in a probability experiment. Sample space is the set of all the possible outcomes of a probability experiment. Event consists of one or more outcomes, and it is a subset of a sample space. This will make more sense as we work with examples. Example 1, identifying the sample space of a probability experiment. A survey consists of asking people for their blood types, O, A, B, and AB, including whether they are Rh positive or Rh negative. Determine the number of outcomes and identify the sample space. And by the way, there is a shortage in blood, so if you would like to donate blood, that it will be a good thing to do. Solution. So based on that, there are 4 blood types, O, A, B, and AB. Each person is either Rh positive or Rh negative. And by the way, I am A positive. I love that, A plus. Okay. A tree diagram gives a visual display of the outcomes by using branches that originate from a starting point. It can be used to find the number of possible outcomes in a sample space as well as individual outcomes. Solution. So the tree diagram, it really helps you see how to generate the sample space. So as I mentioned earlier, we have 4 blood types, O, A, B, AB. So you make it like a tree branch, and then each blood type can be either positive or negative, positive or negative, positive or negative, AB positive, AB negative. And here, what you see here, O positive or O negative, A positive, A negative, B positive, B negative, AB positive, AB negative. The sample space is a collection of all of these outcomes. So the sample space has 8 possible outcomes, which are listed below. So they are enclosed in braces and separated by a comma. And by the way, when you, if you're asked to enter this in a homework problem, and you are asked to list them and they're not in multiple choice, make sure that you don't leave a space between the commas. It will be O positive, comma, next outcome, next outcome. Do not enter a space because it's treated as like an entry and it will count it wrong. So just to give you the heads up. So an example of a simple event. And a simple event is an event that consists of a single outcome. So for example, tossing heads and rolling a 3. So tossing heads, you can either get heads or tails. Those are the outcomes when you flip a coin. You either get heads or tails. When you roll a die, so after you flip the coin, you roll a die, and the choices are, this is a 6-sided die. So the choices for when you roll a die are either 1, 2, 3, 4, 5, or 6. So you can get head first and then the number 1 when you roll the dice. Head 2, head with a 3, head 4, head 5, head 6. So these right here are the outcomes that they all have heads. Or you can have tails, and it can be a tails with a 1, a tail followed by a 2, a tail followed by a 3. So these are the outcomes when you have tails. So all of these 12 outcomes, each one of them consists of a single event. Each one of them is a single event, but together they're outcomes from the experiment. An event that consists of more than one outcome is not a simple event. So for example, if an event is tossing heads and rolling an even number, since you have several options for that, as it is listed in here, you can get heads with a 2, heads with a 4, 2 and 4 are even numbers, heads with a 6. So this one right here is not a simple event. Now let me go back to this one real quick. To highlight, a simple event is like one of a kind. If you're looking for tossing heads and rolling a 3, there is only one outcome that satisfies that condition, heads 3. Another example, it could be tails 5. There is only one of the outcomes that is as specific like that, that is tails followed by a 5. But in this second description here, an event that consists of more than one outcome, if you're looking for tossing heads and rolling an even number, there is more than one outcome that satisfies that event. So therefore, the second part is they're not simple events. So now we're going to identify simple events. Determine the number of outcomes in each event, then decide whether each event is simple or not, and explain your reasoning. So number 1, for quality control, you randomly select a machine part from a batch that has been manufactured that day. Event A is selecting a specific defective machine part. So event 8 has only one outcome. There is only one that has a specific defect. So choosing the specific defective machine part, so the event is a simple event. I do have to admit that that might not be the best, my favorite example of a simple event. I honestly prefer the one from the previous, from the coins and the dice. So anyway, this one would need to grow in me a little bit more years. Next, you roll a 6-sided die. Event B is rolling at least a 4. So if you roll a die, and then it says the event B is rolling at least a 4. So the outcomes that you can expect from a 6-sided die is you can either roll a 1, a 2, a 3, a 4, a 5, or a 6. So if the event is looking for rolling at least a 4, that means that you can roll a 4 or a 5 or a 6. Therefore, there are 3 choices, 3 outcomes that satisfy this event. Therefore, event B has more than one outcome, so it is not a simple event. And I love the graphics here, okay? A 4, a 5, or a 6. Next, the fundamental counting principle. I love this principle because it does save you so much time. And this principle is, it helps you determine the number of ways, the number of events. The number of ways in which 2 events can occur, but it can also be for more than 2 events. So if one event can occur n ways and a second event can occur n ways, the number of ways the 2 events can occur in a sequence is m times n. I know it sounds kind of abstract, but when you look at an example, it will be really good. Can be extended for any number of events that occurred in sequence. That means one after the other. So here we go with this example. You're purchasing a new car. The possible manufacturers, car sizes, and colors are listed in the table. So here they're looking at the manufacturers are Ford, GM, and Honda. Personally, I'm offended that Toyota is not there, but that's fine. Car size, compact or mid-size, color, white, red, black, or green. Yes, my car color is not there either, but that's fine. So how many different ways can you select one manufacturer, one car size, and one color? Use a tree diagram to check your results. So this is really like if you go to the dealership and you go to those, it's like these are your three choices. What are you looking for? So you're able to say you will get out of there, hopefully, with one car, one type of car. And if those are the choices, this will just tell you how many choices do you have to choose from. And sometimes there are just too many and we get overwhelmed. Anyway, so since there are three choices for a manufacturer, so we put a 3 there. There are two car sizes, so you put 2, and there are 4 colors. So using the fundamental counting principle, you have 24 ways or 24 options to choose from. So to illustrate that, it's good to use a tree diagram. So this is how the tree diagram will look like. So you forward and you will say, well, do you want to choose a compact or do you want a mid-size car? Usually Texas will go for mid-size, just saying. And then after you choose that, it's like, okay, do you want a white, red, black, or green? Each one of them. So those are all the choices. And there is, let me go back. I thought they were going to show you all the choices. So each one of these, you have 3 here. That's this one, 3. Compact 2. The other one, you have 4 choices. So if you go through each one of them, it can be 4 compact white. That's 1. It can be 4 compact red, 4 compact blue, or black, I don't know. I don't recall what that one was. 4 compact green. So each one of this is going to have 4 choices, and you're going to do this 6 more times, 5 more times. So a total of 6 times. That's how you get the 24 choices, the 24 ways. So the next example. We're also using the fundamental counting principle to find the following. The access code for a car's security system consists of 4 digits. Each digit can be any number from 0 to 9. So and the digits, when you count from 0 to 9, okay, you can count with me. So you would first finger 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you will have 10 choices. So when it says from 0 to 9, there are 10 choices. So how many access codes are possible when each digit can be used only once and not repeated? Case number 2, each digit can be repeated. Case number 3, each digit can be repeated, but the first digit cannot be a 0 or 1. So let's look at each one of this. So the first one, because each digit can be used only once, there are 10 choices for the first digit. There are the 9 choices, because you already used one of the 10 for the first one. You have 10 to choose from. For the second one, you have 9 to choose from. For the third one, you have 8 to choose from, 8 left to choose from. And then for the fourth number, you have 7 to choose from. So therefore, using the fundamental counting principle, you have 10 times 9 times 8 times 7. That is 5,040 possible access codes, possible choices, combinations, or ways. The second one, because each digit can be repeated, keyword repeated, there are 10 choices for each of the 4 digits. 10 for the first one, 10 for the second, 10 for the third, 10 for the fourth. Therefore, 10 times 10 times 10 times 10 is 10 to the 4th power, or you can go straight to 10,000 possible access codes. Third case. Because the first digit cannot be a 0 or a 1. So if you remove a 0 and 1, you can only choose from having a 2, a 3, a 4, a 5, a 6, a 7, or 8, or 9, I'm sorry. So that gives you 8 to choose from. That is why you start with an 8 here. You remove 2, which are the 0 and the 1. The other ones do not have any conditions or any restrictions. Therefore, you have 10 for the second choice, 10 for the third, and 10 for the fourth number. So you multiply all of those 8 times 10 times 10, and that gives you 8,000 possible access codes. Okay. Types of probability. The first one is a classical, and I call this the book one, the big book version of it. So this is based on theory. So theoretical probability. Each outcome in a sample space is equally likely to occur. So for instance, if you're looking for the probability of an event, it will be the number of outcomes in that particular event divided by all the possible outcomes in the sample space. So here is an example of to find classical probability. If you roll a 6-sided die, find the probability of each event. So the probability of rolling a 3. When you roll a 6-sided die, there is only one of those 6 numbers that is a 3. So the probability of rolling a 3 is going to be 1, because there is only one 3, 1 out of 6. Number 2, the probability of rolling a 7, it only goes from 1 through 6. It only is a 6-sided die. So how many of those is a 7? None. None equals 0. Nada. So 0 divided by 6 is equal to 0. Next, event C. Rolling a number less than 5. Less than 5. What that means is that 5 is excluded. It's only considering the 1, the 2, the 3, or the 4. So therefore there are 4 choices, 4 numbers to choose from, 4 out of the 6. That is going to turn into, you have to simplify that fraction. So that becomes one, that one we'll show you here. So event A, rolling a 3. There is only one event. It's a simple event, I'm sorry. So there is only one that is a 3. So the probability of rolling a 3 is 1 out of 6. If you're asked to round it, this one was rounded to 3 decimal places. So they will tell you whether they want a fraction or they want a decimal, and the fraction must be simplified and just round it according to the decimal places if they ask you for decimal places. These lines here, they're called approximately, because we're rounding is an approximation. Next, the probability of rolling a 7. None of the outcomes is a 7. So 7 is not in the sample space. Therefore, 0 divided by 6 is 0. Nada. Event C. Rolling a number less than 5. So event C, it can be a 1, a 2, a 3, or a 4. Again, 5 is not included because it doesn't say a number less than or equal to 5. So it's going to be 4 out of 6. If you were to simplify this fraction, divide them both by 2 because they're both even numbers. As a fraction, you will answer 2/3. But it seems that here, even though it wasn't mentioned, it was rounded as an approximation to 3 decimal places. Again, it's not always 3 decimal places, it's whatever they feel like asking you, okay? Next, So types of probability, we have now the empirical. The other one was the book version. The book one, equally likely. This one is empirical statistical probability. Ooh, that sounds so fancy. So empirical means done is the practical one. So based on observations obtained from probability experiments. So empirical is the ones that they perform experiments. So it is based on the relative frequency of an event. And I think you have heard that quite a bit. The relative frequency of an event is how many you have of each type divided by the total. So that's still the same way in this section. So it will be the frequency of the event, F, divided by the total frequency, that before it was the sample size. So N is the sample size lowercase and is the sum of all the frequencies. So hopefully that will give you good flashbacks. Next. So here, finding empirical probabilities. A company is conducting an online survey of randomly selected US adults to determine how they read books during the past year, if at all. So far, 1,490 adults have been surveyed. The pie chart shows the results. Note that the digital books include ebooks as well as audiobooks. I love audiobooks, by the way. What is the probability that the next adult survey read only print books during the last year? And this is based on a Pew Research Center from September 2016, Book Reading 2016, in case you want to look it up. Okay, so here we go. We have this pie chart, beautiful colors, by the way. So, and it is about how many read a book, print, audio, anyway, digitals. So let's turn to the next page. So it says, note that the responses are not equally likely to occur and are based on observations. Okay, so notice that they are not all the same number. That's what it means, but they are not equally likely to occur because they all have different numbers. The pie is not divided equally. So next, you cannot use the formula for classical probability, but you can use the formula for empirical probability. The event is a response of read-only print books. The frequency of this event is 578. And then the total of the frequencies will be the sum of all people that were surveyed. And remember that it was 1,490. So the empirical probability, again, we have to use empirical because the pie was not divided equally. So the empirical probability that the response of the next adult is read-only print books is 578, the one for that particular category, divided by the total. And again, the person that made this PowerPoint, they love 3 decimal places. So just give it to them. You divide and put the 3 decimal places there and follow the rounding rules. Next, using a frequency distribution to find probabilities. So a company is conducting a phone survey of randomly selected individuals to determine the ages of social networking site users. So far, 975 social networking site users have been surveyed. The frequency distribution shows the results. What is the probability that the next user survey is 23 to 35 years old? Adapted from Pew Research Center. Okay, so we have the ages here, frequency, the sum of the frequencies, which is the sample size, is given. Okay, so solution. Because the responses are not equally likely to occur and are based on observations, you're going to use the formula for empirical probability. So the event is a response of 23 to 35 years old. The frequency of this event is 312. So let me go back to that slide so that we can see it again. So here it says, what is the probability that the next user survey is between the ages of 23 to 35 years old? If you look in here, that's 312. and the total or the sum of all the frequencies is 975. So the total of the frequencies is 975. That's what I just said. So the probability, and again, this, the notation is important. The probability of the ages being between 23 to 35 years old, close the parentheses, is 312 over 975. And it seems that this one rounded to 2 decimal places. Okay, the law of large numbers. As an experiment is repeated over and over, the experimental probability, the experiment of an event, will eventually get closer to the theoretical or the actual probability of the event. So the more you perform the experiment, the closer you're going to get to the book answer, basically. So as you flip a coin so many times, at the beginning, you might get, oh, maybe heads, maybe tails. So, and in here, they're looking for the probability of tossing a head. But if you do it so many times, you look in here, the number of tosses at the beginning, you were just getting different results. So the probability of getting heads until you do it so many times, 150 times, and you will see that it will get close to 50% of your tosses are going to be heads and 50% are going to be tails. So that's what it comes to, 50% each. It is done so many times, so it's based on the law of large numbers. The more you do it, the closer you're gonna get to the theory. Okay, so the third type of probability is subjective probability, and that one is based on intuition, educated guesses, and estimates, which is really what is going on now with this virus that we have. It is a lot of subjective probability that they're trying to use predictions based on the experiment. So they're really using to see if they can get to be something that they can predict. So a doctor may feel, an example of this, a doctor may feel a patient has a 90% chance of a full recovery. So that's pretty good. So here it says classify this statement as an example of a classical probability, empirical probability, or subjective probability, and explain your reasoning. The probability that you will get an A on your next test is, you will say 90%. And you might say that because you made an A on the first test. So you're saying, well, I usually make A, so I'm gonna make at least a 90 on this test. Okay, so this one is a subjective probability. So you usually do make an A, but what if that day was not your best day? There are so many variables that are hard to control that's why it's called subjective probability. You did an educated guess and you will go for the A, but you may not get it, okay? We hope that you do on this test. Next, the probability that a voter chosen at random will be younger than 35 years old is 0.3 or 30%. Okay, this one is empirical. So they just study the people that voted, and it's an experiment. So most likely it's based on a survey. And that's why it's an empirical probability. Third one, the probability of winning a $1,000 ticket raffle with one ticket is 1 in 1,000. Okay, it's usually lower than that, by the way. That one will not be that bad. So this one will be a classical probability. That's what will usually happen, and these tickets are equally likely to occur or be selected. Next, the range of probabilities. The probability of an event E is between 0 and 1 inclusive. Okay, it can be a 0 and it can be 1, and numbers between those two. So this is a different way of using inequalities to express that the probability of an event can be between 0 and 1 inclusive. That means that it can be 0, it can be 1. So if it is 0, that is like, it will be impossible. Like getting a 7 from a 6-sided die, that one is impossible. Or if it's a little bit higher, you can say, oh, that's unlikely because it's low. 50%, just an even chance. 50-50, likely, that it could happen. And the 1 is like, oh, definitely certain it will happen. Okay, so complement of an event, complementary events. Okay, sometimes we have this might be a learning curve on this concept. The set of all outcomes in a sample space that are not included in event E. So this right here is using a Venn diagram to display and present the concept of complement of event E. So if the rectangle represents the universe, so here event E is everything that is inside of that pink circle. The complement is what is not inside the pink circle, but is still part of the outcomes, the possible outcomes. So that's what you call complementary events. So, and they use the E apostrophe or E prime. E prime, I shall say, E prime. Sometimes other authors may use a bar. So the probability of the event plus the probability of the complement of the event, they have to add up to 1, okay? So they complete each other. It's just like that movie, You Complete Me. Okay, Google it. What movie was that? So if you know the probability of an event and you want to know the probability of the complement, since they both have to add up to 1, 1 minus the probability of the complement will give you the probability of the event. And if you have the probability of the complement and you wish to find the probability of the event, it will be 1 minus the probability of the event. I know, maybe by now you're getting a headache. Okay, let's work on this. Find the probability of randomly selecting a social networking site user who is not 23 to 35 years old. So basically is everything that is not this 312. So it can be 156, it can be 254, it can be 195 or 58. There are two different ways to approach this question. This one, if you find the probability of what you are not looking for, which is the 23 to 35, because it says that it's not, but if you find the probability of being that answer between 23 and 35, that will be 312 out of the total. So the probability of not, again, by having the word not, that means that is the complement. It's still part of the frequencies and the survey, but you don't want that. So 1 minus what you do not want will give you the value of what you do want. And this is easily entered in the calculator, or just 1 minus, this one was 0.32, that gives you 0.68. Yes, if you did not want to use a complement, you could just have added 156 to 254 to 195, 258, and that will give you the same answer. As long as you divide the other ones by 975, you will get 0.68. So you can pause the video and give it a try, and you should get it. Next, using a tree diagram. A probability experiment consists of tossing a coin and spinning the spinner below. The spinner is equally likely to land on each number. Use a tree diagram to find the probability of each event. Event A, tossing a tail and spinning an odd number. Event B, tossing a head or spinning a number greater than 3. So this is a tree diagram. These are all the choices because the spinner has 8 numbers. So these are all the choices. You can get the head followed by spinning a 1, a 2, a 3, all the way to 8. Tails 1 through 8. So this is, if you were choosing everything, this is the sample space. So event A, it only wants the tails and the 1, 3, 5, and 7. So that is event A. So there are only 4 outcomes for what you are specifically looking for in event A. So the probability of tossing a tail and spinning an odd number. So odd numbers are 1, 3, 5, and 7. So there are 4 of those out of the 16 options. All of this, when you add it up, there's 16 outcomes. So 4 divided by 16 is 1/4 as a simplified fraction, or turn it into a decimal. Next, event B. The probability of tossing a head or spinning a number greater than 3. Tossing a head, so head and a number greater than 3. So it seems that there are, it says or. It said tossing a head or spinning a number greater than 3. So when it says or spinning a number greater than 3, you will also take into account the tails. It doesn't say and. If it's and, you will not include the tails. But since it says or, the tails are included. Okay, so the event B will consist of these 8 plus 5 more. There are 13 of those. Out of all the outcomes, 16, and we're going back to approximately equal to 0.813, 3 decimal places. Next, using the fundamental counting principle. Your college identification number consists of 8 digits. Each digit can be 0 through 9, and each digit can be repeated. What is the probability of getting your college identification number when randomly generating 8 digits? Okay, so each digit can be repeated. So there are 10 choices for each of the 8 digits. 10 choices because they can be repeated. So the first one, it can be any numbers from 0 to 9. That's 10. And you have 8 of those. So that's 10 to the 8th power, because you add the number of times that you're repeating them, or that is equal to 100 million possible identification numbers. So that is how many ways, okay, or the number of outcomes. Then only one of those, so that's why this one is usually a little tricky. Only one of those is your unique ID number. Nobody has your social security. Nobody has your student ID. That's your unique number. So your ID number is 1 in this amount, and you will get all of these zeros in decimal places. So you are pretty special. You're very unique. And that's it for this section. I hope you enjoy it, and make sure that you try the homework. It is absolutely beautiful. Thank you. Goodbye.